Hey there, chemistry class. Today I want to talk about double replacement reactions. So you've already seen these, you've already done some general forms and descriptions of them. And today I want to talk about some more details. So what we're going to do today is review identifying double replacement reactions. How do we know we're looking at a double replacement reaction? How do we determine what the common products are of a double replacement reaction? What the products of the reaction are going to be, the actual chemical products of the reaction. And lastly, we'll preview determining how we can tell if something is going to be a precipitate in a double replacement reaction. So, the double replacement reaction is the one where we have two ionic compounds. So, in this case, we have A, B, and C, D. And in this type of reaction, both of the cations are going to change places. So remember, in the single replacement reaction, we had a single metal and a compound. Here we have two compounds, and the cations or the metals are going to switch places. So when we see that happen, here's our metals. Here they are switching places, and then they're going to recombine with the anions that we have or the nonmetals that we have. Okay, so this is what the completed reaction would look like, right? And we see that AB plus CD yields AD plus CB. And again, remember when you're writing the products of these reactions, you always have to write the metal first and then the nonmetal. By this point, that should be pretty ingrained in you as far as writing ionic formulas are concerned. We always write the metal first and then the nonmetal. Now, to try to determine what the products are going to be, there's a couple of different ways you can approach this. What I like to do is to write the charge on top of each of the ions that we have in the products. So I know it's going to be A is going to be positive. I'm not sure what the charge is. This is obviously just a general formula, but I know A is going to be positive, B will be negative, C will be positive, and D will be negative. And then I can, if I'm practiced at this, I can determine what AD is going to be and what CB is going to be based on balancing the charges between A and D, and likewise between C and B. Now, if you still need a little bit of work on this, if you're still trying to determine how to write these formulas, another way you can do this is to bring the compounds down into their ion form. So we have A and whatever the charge is for A, and then we have B and whatever the charge is for B. And then we're going to bring down C and lastly D. And when you set them up this way, then you can do a simple crisscross. So A has to go to D and C has to go with B, and then you can balance the charges that way. Let's take a look at this in action. So the picture that was in the title slide for this presentation was the reaction between potassium iodide and lead to nitrate. That's what results in that beautiful yellow precipitate that we see. So in this instance, A is potassium, B is iodide, right? C is the lead, and D is the nitrate. So again, what I'm going to do is write on top of each of these elements their ionic formulas, or the ionic charges rather. So looking at the periodic table, I can see that potassium is a positive 1, and the iodide is going to be a negative 1. And when I look at the periodic table, I can see that lead is a transition metal. So I'm maybe not quite sure what the charge is going to be on lead. So instead, I'm going to look at nitrate first. And if I look at nitrate, I can see that nitrate has to be a -1. And because nitrate is a -1, and I have two of them in my formula, I have a total negative charge of 2 minus. So that tells me that in order to balance out that negative charge, the lead must be a 2 plus. Okay, and again, we're talking about balancing charges here. So the lead has to be a 2 plus in order to balance out the two negatives that come from each of the nitrates that we have. Okay, so in looking at this, I can see a relatively simple product that I'm going to have, right? I have potassium combining with the nitrate, and they're just a +1 and a -1. And again, another good way to remember doing this is to think of doing insides and outsides. right? So you're going to be combining the two inside elements and the two outside elements or ions in this case. So the potassium combining with the nitrate, again, is a 1 plus and a 1 minus. So that's going to result in KNO3. All right, and now how about the other compound that's going to form? Now remember, we have to put the lead first because it's the metal, it's the cation. Okay, I have lead 2 plus and I have iodine, which is 1 minus. So what will the formula be? Again, you can go ahead and do the little accounting that we've always been doing. 2 plus is the lead. That means I'm going to need two of the iodides in order to balance out the lead. Okay, so two pluses and two minuses. So my formula for the lead iodide is going to be PbI2. Okay, now you'll notice that I didn't put any states of matter in the products. And that's because I want to still keep that a bit of a mystery to you because one of these products is the yellow precipitate that we saw. And the other one is still just dissolved in the water. And I kind of don't want to tell you which is which right now because that's part of your lab that's coming up. So just realize that I left the states of matter out of the equation on purpose in this case. Okay, so let's see now if we can determine, based on that general form, which of the following examples that I'm going to give you now, which of these are double replacement reactions? So let's take a look at the first one. The first one has the reactant magnesium oxide. So can this be a double replacement reaction? And the answer is no, right? I have to have two ionic compounds in order to make the switch, in order to be a double replacement reaction. More than likely, this is probably going to be a decomposition reaction, right? Because I only start with one product. So it's probably going to decompose into magnesium and oxygen. Okay, how about this one? I have FeSO4 and nickel. Okay, so I'm getting closer because I have an ionic compound in iron 2 sulfate. But my other uh, part of the reactant here is just a single metal, right? It's not another compound. So this is not a double replacement reaction. This is what we just finished looking at, the single replacement reaction. Okay, next I have C4H12 combining with oxygen. So this should just be like a red flag in your brain right now, or I should say like a flaming red flag, right? Because this is clearly going to be a combustion reaction. And you should know that the products of the combustion reaction, right, are going to be carbon dioxide and water, by the way. Okay, so let's take a look at this last one. Sodium hydroxide in solution combining with barium sulfate in solution. So it looks like I have the components that I need here, right? I have a cation and an anion, an ionic compound in solution, and another cation and anion in solution. So yes, this is going to be my double replacement reaction, right? So only one of these was a double replacement reaction. So you should be able to recognize that based just on what the reactants are, okay, at this point. Great. So now, what do double replacement reactions produce in general? Before we discuss the specific products, like we did in the example before, um, in general, a double replacement reaction is going to form one of three types of products. So it's either going to form a gas, okay, not exactly what you see here, but you know what I mean, and hopefully the visual will help you remember what you see here. Or it's going to form water, and that happens when we do acids and bases. So I'm not really going to talk about that too much right now. And the last possibility for a double replacement reaction is the one that we are going to focus on, and that is the precipitate, right? So that is that beautiful yellow precipitate that I showed a picture of in the title slide. Right. So what we are going to focus on, as I said, are the reactions that form a precipitate. Okay. So the question is, how can we tell which of our products is a precipitate? They can't both be precipitates. I'll leave you with that. I'll let you figure out the logic of that in a minute. But they can't both be precipitates. So one of them has to be a precipitate, and the other one has to be soluble in water or able to dissolve in water. And when I say dissolve, I want to clarify here what happens when a compound dissolves in water, specifically an ionic compound. So, in the beakers here, I have an example of an ionic compound dissolving in water. And let's say, for simplicity's sake, since we're so used to it, we'll call this sodium chloride. Okay, so we put a little piece of salt into water. Clearly, we have, like, again, by now, you're so used to seeing water molecules. We put some sodium chloride into water, and what starts to happen? These hydrogens, which are positively charged, are going to come and start grabbing at those chlorines, which are negatively charged. And this oxygen, which has a partial negative charge, is going to start grabbing at the sodiums, which have a positive charge. And what's going to happen, as you can see, is that they're going to start to break away. And some substances do this better than others, depending on how strong their bonds are and how water is able to overcome the strength of those bonds. And for things like salt, table salt, sodium chloride, their bonds are not particularly strong compared to the pull of the water molecules. And so that's why it's so easy to dissolve salt into water. And the ions just float around in the water very easily and get pulled apart by the water molecules until it basically looks like there's nothing in the water, right? And that's because the sodium ions and the chlorine ions are so small, they're the size of atoms, that we can't see them in the water. It just looks clear. Okay. So, what we're going to figure out, though, is which compounds that we can create from double replacement reactions will dissolve in water, like sodium chloride, and which ones won't, because not all ionic compounds can dissolve in water. Again, like you saw with that yellow precipitate. And when they can't dissolve in water, that's when we have the formation of the precipitate, the solid that forms from the combination of two solutions. So, what we're going to do to figure out which compounds are going to dissolve in water and which compounds are not going to dissolve and are going to be our precipitate is we're going to use a set of rules. And of course, they're called solubility rules because they have to do with how compounds can dissolve or be soluble. Those rules are general guidelines to tell us or help us to predict which compounds will be able to dissolve in water and which ones won't. And just like your activity series for single replacement reactions, the way we're going to find out these rules is through lots of experiments. So, I'm going to do a set of over 70 experiments, combinations of solutions in order to figure out which ones create products that will dissolve in water and which ones create products that won't dissolve in water. The good news for you is you don't have to simulate these reactions. You're not actually going to be doing 70 of these reactions. I'm just going to give you the data, and you are going to do the hard part. You're going to figure out the patterns in the data. Okay. So for tomorrow, or yes, for tomorrow, right now, I'd like you to work on the pre lab. So, what I want you to do is take a look at that first page, which is asking you to write a preliminary claims evidence reasoning for the reaction of the potassium iodide with the lead 2 nitrate. So I don't want you to be fancy here. I don't want you to even necessarily look anything up. I want you to write as far as you know, as far as we've discussed so far and you've seen in your reading. Okay. Then what you're going to do is just refresh your memory and review a little bit formula writing. So you're going to take the compound by name and write out the chemical formula, and then also write out what the cation is and what the anion is. And this is for the set of solutions that we will be using to form the reactions to determine the precipitates. What's going to happen tomorrow is I'm going to give you the data, and then you'll be able to find patterns in the different combinations of solutions that we have. Okay, so that is what we'll see tomorrow. This is an example of the data that you'll actually see. So this is a pretty cool picture of this kind of swirling green blue precipitate that we have when the two compounds reacted. Okay, so get to work on the pre-lab. Review section 9.2 on double replacement reactions. Go to the section 9.2 page in the notebook. And if you need to, watch another video, check another website out, do some practice if you want. That's there as well. Okay. And be ready to write the products of the double replacement reactions. That's what's going to be part of figuring out the lab is finding the patterns in the data and being able to write the products of the reactions. Okay, so as usual, any questions, any problems, anything at all, please let me know what you need.